It is Tuesday, November 24th, and we're going to continue our discussion of inferential statistics. Yes? Before I get started, are there any Yes, hello. When will homework 6 be finished and graded and posted? I would imagine the TAs are ready to get that off their plate. I will talk with them this afternoon and see. But I would imagine that as homework 7 was in yesterday, that they are probably pretty much done with it and ready to post it. Because I'm sure they want to take a break this weekend as well. Yes? On the clickers? Yeah, we didn't have a topic 3 on clickers. So it's going to be your highest 6 out of 7. Because we went through topic 3 very quickly and didn't have a whole day on that. So you're looking at your gradebook and you're making sure that everything is accurate and as you think it should be. And if it isn't, you're going to let us know. When's your next midterm? Next Thursday, correct? So we've got today's lecture and we've got next Tuesday's lecture and then it's over. And then you've got a midterm on the Thursday. We know that you will want to know what you did on that midterm as soon as possible. I'll be begging the TAs to cancel all their social plans and to focus only on grading your midterms so that you have the information that you need in order to decide whether you need to take the optional final exam. Because the final exam is optional, right? If you take all 4 exams, your lowest multiple choice score will be dropped and your lowest written score will be dropped. So if you've taken the 3 midterms, as soon as we have that posted, you will know what your grade is. And then you can choose whether or not you want to take the final. If you've missed a midterm for any reason, obviously that's in your gradebook as a big fat 0, and you would want to take the final. The final would no longer be optional for you, right? Because you would want to replace that big fat 0. So we will get that information back to you as soon as possible. We understand that you will be dying to know how to spend your finals week. Just another comment. So the midterm is next Thursday. You're going to bring a pencil, you're going to bring a Scantron, you're going to bring a 1-page cheat sheet. You may also bring a simple or scientific calculator. You will be doing some data calculations as you've been doing on your homeworks. Means, standard deviations, z-scores, n's, small groups like 5, 6, 10, 12, and not to huge levels of precision. I believe it's only in the multiple choice section, and it's things like, is the mean 1, 2, 3, or 4? So it's not, is it 1.01793 or 1.091794? Or, it's not to huge levels of precision. Just so that you can demonstrate that you understand what you are doing when you calculate a mean, when you calculate a standard deviation, when you count an n. Because you've been practicing those on your homework, and those should be formulas that you now know and own and understand. Yeah?
So on that note, the material is covered by the third midterm, everything after
Yeah, so the third midterm is the descriptive statistics, inferential statistics, and presenting results. So it's what we've been doing on topic 7 and 8. That's the focus. Obviously, there's going to be label your predictive variable, critique the construct validity, all of those concepts that we've been living with for weeks now. So feel free to bring a scientific or a standard, a simple calculator. I'm asking you not to bring a graphing calculator because graphing calculators do it for you, where you enter the data and it tells you the mean and the standard deviation, because you live in a time where you're never going to have to hand calculate statistics ever again. Lucky you. But the point of this is just that they're not that hard, and you can do them, and you can demonstrate that you understand them. Was there a question over here? Yeah.
So for the written part of the exam, should we expect to be like problems like that, or should we just expect to be like
So for the written portion of the exam, the majority is going to be exactly as you've seen before. Here's a research summary. But like last time where we were focused on like critiquing the threats to internal validity, This time we're going to be focused on interpret the results. Okay? So there's, the standard, however many questions of, label it, what are the levels, critique the variables, but then the extra bits will be, how would you interpret these results? What is a sentence? Because you're doing that on your homework, right? Where you're practicing writing these interpretation sentences. That's what I'm going to ask you to do on the exam.
So on the final,
Mm-hmm. Okay, so on the final, if time management has been a challenge for you in these exams, the final is scheduled for 2 full hours. It's the same length exam. It's 40 multiple choice and those 2 written portions. So you're going to have an extra 40 minutes for the final exam. So taking the final exam, you are, if time management has been a concern, then you should do fabulously well on the final exam. You're welcome to spend the entire final exam period just working on the written portion and just submit the written portion. They are independent exams, so you can just do the multiple choice, you can just do the written, you can decide what you need to do in order to raise your grade and get the grade you want. 60% of your grade is still out there. The midterm 3 and the final are 60% of your grade. I know that this sort of material seems like a lot to begin with and seems very confusing and very overwhelming, and that by this point in the quarter, you guys should all be just, you've got it. You look at those research summaries and you know exactly how you're going to phrase the critiques so that the TAs just do great big check marks. And so taking the third midterm and the final, that's 60% of your grade that you can demonstrate that you now know all of this material. Yes? On the third midterm, like I said, I'm going to ask the TAs to do it as quickly as they can. We've got a week between the third midterm and the final, so you'll have it in plenty of time before the final exam before the final exam. But we'll try to get it done in the usual, which is like 3 or 4 days. Yeah? So the podcast for last week, I think I just did it this morning. I think it's up. Okay? But let me know if it's not. Yes? I'm sorry, I missed the critical word there. When are the exam viewings? Those should be being announced, and they will be ongoing. I don't know. I don't know if there are any planned for this week. It seems like it's a very short week, so maybe not this week, but certainly next week. All right. Are you guys you're just trying to avoid the calculating inferential statistics, aren't you? It's like, let's see how many questions we can think of asking, because, oh my goodness, she didn't forget that we were going to calculate inferential statistics. We looked at the first few of these slides at the end of Thursday. I'm going to go through them incredibly quickly. Okay? So we're talking about inferential statistics. Just quickly. What do inferential statistics allow us to do? Make a decision. What's the decision we're making? Reject or fail to reject the null hypothesis. What if we've got like 2 groups? What are we asking? If we've got the means of the people who had to push someone and the means of people who had to pull the lever, is there a significant difference between the groups? Is there a reliable difference between the groups? Do we think there's a real difference between the groups? That's the sort of thing that inferential statistics allow us to do. And we talked about that kind of conceptual introduction, and we're now coming into talking about calculating them. So when we talk about calculating inferential statistics, so you will be calculating descriptive statistics. We've already done that. We know that, right? Then there is the calculating an inferential statistic. These are the steps you go through in data analysis. You then take your calculated inferential statistic and you look up the p-value. That's going to make sense in about an hour. You then make your decision, reject or fail to reject the null hypothesis. So let's talk about continuous outcome data, where we've got our outcome was measured along a continuum with numbers. So you've calculated means or standard deviations for your groups. So you've got two groups and you've calculated the means, and you want to know if those means are significantly different, if there's a reliable difference, if there's a real difference. So let's take a look at that. So here was our data for that we gathered with the clickers, where you said whether you would save 5, and if you were in the close group or the distant group. This is how many people were in those groups. This was your decision on a scale of 1 to 5, whether you would save 5, with the 5 being, I would definitely not. No, I would definitely. 1 was definitely not, 5 was definitely. We want to know, is this difference big enough to say that it's a real difference? It's different. What else could it be due to? Every time I draw a sample, just chance, just sampling error, just random, every sample's going to be different. So we want to know, is this just, every sample's different, or is this a real difference? So we looked at, we could graph it, and we could exaggerate graphing it. But what we really want to do is look at it objectively and compare those. And so we said, here are what those descriptive statistics describe, and we want to know, do those look like they come from the same population, or do they look like they are two samples drawn from two different populations? Yes, we're getting very close to where we were. So we said we're going to calculate this T ratio. The T is the difference between the group means divided by roughly the average variability within each group. And then I showed you the formula. And take a deep breath, the anxiety will pass. Oh, no, wait. Where's the formula? That's coming up. Okay. So we thought about it. If the null hypothesis is true, the null hypothesis always states that there's no difference, there's no relationship. So the mean of group 1 is going to equal the mean of group 2. Any number subtracted from itself is 0. So the T ratio would be close to 0 because the numerator would be a 0. If the difference between the group means is close to the difference within the groups, any number divided by itself is 1. And so if the T ratio is close to 1, probably it's just due to sampling error. Okay, now here's the deep breath. Take a deep breath. So that's mean of group 1 minus mean of group 2. That's how we compare the two groups, the group means. And then this we said was, let's see, we've got the sum of squares, which was a number that we came across when we were calculating the standard deviations. Divided, so we're adding up the two sum of squares and dividing them by the sample sizes. That's averaging them. This is basically finding the average standard deviation. We've got a little bit of an extra factor there that dings us if we have a very small sample size. Yeah. SS is the sum of squares. And that was a number that we came across when we were calculating our standard deviations. You are not going to have to hand calculate a T or any inferential statistic. We've got wonderful programs that would do that for you. Let's go back to the example of that really inane example. The inane example about the first grade students and the second grade students. Yes, we took a sample of 5 first grade students and a sample of 5 second grade students. We asked how old they were. So I've got the means and standard deviations and sums of squares. So let me just show you. I'm just going to click through and it's all going to plug in. Right? So we'd plug in those numbers and we'd say 6 minus 7, and we would start simplifying those numbers there, and we would get a negative 2.97. Okay, so our T is negative 2.97. What does that mean? We don't want a T. What do we want? We want a P. So we've calculated the T. Okay. So let's talk a little bit about the properties of a t-ratio. So it's a single number. It's that ratio of the difference between the two groups, the difference between the groups, and the variability within the groups. Okay. Let me talk about the t-test for a little bit, what we would do here. So, Christmas is coming up. If you know any statistics majors, best gift ever is a bingo drum. You know the idea of a bingo drum? You fill it with ping pong balls? Yes? And you wind the crank and you pull out a ball from the little gate? Yes? Okay? Best gift ever. All right? So what a statistics major is going to do is he's going to take all of the ping pong balls that came with it that said like B2 on them, and he's going to throw those away. And he's going to go and buy like 1,000 ping pong balls. So we're going to make a population with n equal to 1,000. We are going to make a perfect normal distribution. Let's see, favorite number is 100. So I'm going to make a normal distribution with a mean of 100 and a standard deviation of 10 because those numbers are easy. So how many ping pong balls on how many ping pong balls am I going to write numbers between 90 and 110? 68%. I've got 1,000 ping pong balls. So on 680, I'm going to write numbers between 90 and 110 and throw them into that cage. Because I'm going to make a perfect normal distribution. So we know that 68% fall between plus and minus 1 standard deviation. How many am I going to write between 80 and 90? Do you remember? You wrote this out, right? You're going to have to do this a lot with your z-scores coming up. So it was 34 here, 13.5. So 135 between 80 and 90, and another 135 between 110 and 120. Do you see what he's doing, right? And then, what was that last? So 20 between 70 and 80, and 20 between 120 and 130. We're nearly done with our population, right? We've got 10 ping pong balls left. And so we're going to write a couple of numbers above 130 and a couple of numbers below 70 and pop those in. We have the perfect normal distribution. We have a population that is perfectly normally distributed. Now the fun really begins. This is like Saturday night. Parents' basement. Hot cocoa. You're going to draw a sample. You're going to draw 2 samples from this population. So let's see. Let's start with samples of size 10. So let's say he draws his first sample and it has a mean of 99 and a standard deviation of 9. That sounds about right, yeah? You'd expect it to estimate his underlying population because he's got all of these ping pong balls here at 100 and 101 and 99. And then he draws another sample, also of size 10. And let's say this is a mean of 101 and a standard deviation of 11. Is his null hypothesis true or false? The null hypothesis states there's no difference between these groups. These groups were drawn from the same population. Is his null hypothesis true or false? True. He knows that, right? He is drawing them from the same population. So we know the null hypothesis is true. We're not going to know that when we're actually going out into the world and gathering data, but for what he's done, he knows the null hypothesis is true. So we're going to calculate a t. What do we get for this t? Difference between the means, let's see, 101 minus 99, divided by roughly the average of 9 and 11. What does that equal? 2 divided by roughly 10. What does that equal? 0.2. Okay? He's going to do it again. He's going to draw another 2 samples. He's going to stay up all night long and draw sample after sample after sample. So let's see, his sample 3 had a mean of 100 and a standard deviation of 9, and sample 4 had a mean of 100 and a standard deviation of 11. What's his t? It's 100 minus 100 divided by the average of 9 and 11, which equals 0. So while he is calculating these, he is charting them. And guess what? Guess what he finds? T-values are normally distributed. Isn't that wonderful? And so he's got this normal distribution where most of them are at 0. A lot of them are between 0 and negative 1 and positive 1. Sometimes he does draw a sample that's up to 2 or down to negative 2. And it's really unlikely to get a t-value beyond just about 2. Do you understand what he's done? So he has made sure that his null hypothesis is true. He knows he's drawing 2 samples from the same population. He's calculating all of these t-tests. He's then put that out, graphed that, and looked at that distribution, found that it is normally distributed. He now knows, what's the probability of calculating a t between negative 1 and 1? That probability is 0.68, right? What is the probability of calculating a t way out here? 0.05. Is this beginning to seem like it's going to start connecting to what we want? Let's take a look. So, it's a number that is the difference between the groups divided by the variability within the groups. We want it to be bigger than 1 because that is going to be is going to let us decide. Is going to let us reject the null hypothesis. Or if it's close to 0, close to 1, it's almost certainly not going to let us reject the null hypothesis. It can be positive or negative. When it comes to t, we don't know. We don't really care about the value, the sign. The one that we just calculated was like negative 2.97. What made it negative? The numerator. So it was, did we subtract 6 from 7 or did we subtract 7 from 6? Yeah, it makes no difference really. There's no reason that one's group 1 and one's group 2. Yeah. I was estimating the t-value. And it actually is very similar to that formula, because the standard deviation of each of those is the sum of squares divided by n minus 1. And so even though, so it really does, it is really very similar. You're never going to have to hand calculate an inferential statistic. Anyone who asks you to is just being mean. You've got lovely programs that are going to do that for you. All you need to know is, what does it mean? What does this t-value mean? And that's where we're getting to. So the only thing that made our t positive or negative was whether we subtracted group 1 from group 2 or group 2 from group 1. That doesn't mean anything. So we're not worried about, we're not interested in the sign of the t. It doesn't mean anything, it doesn't give us any information, meaningful information. Yeah? Uh-huh. Yep, we're only worried about we're only interested in the absolute value. Yep, we're interested in the absolute value of a t ratio, and we know, we've already decided that if it's close to 0 or it's close to 1, that means that there's no difference. For the 0.2, we knew that if our null hypothesis is true, we're really likely to calculate a 0 or a 0.2 or a 0.7 or a 1 or maybe even a 1.5. If we calculate a 17, is that likely to be from this guy's ping pong drum? No. And that's where we're going. So the probability of calculating that particular t-value, assuming the null hypothesis is true, have all been calculated for us. Those statisticians have sat in their parents' basements and calculated. Do you know what? So he stayed up till 4 a.m. that night. Guess what he did the next night? He did samples of 11. And then the next night, samples of 12. Because it turns out that as the different sample size makes a little bit of a difference for your t-value, and they're a little bit differently distributed. So they've all been calculated for us. They're normally distributed, and what they've done is they have condensed those into the table of critical values that is at the back of every statistics book you've ever picked up, whether you've opened it to that back page or not. So what they've done, here are the distributions that he calculated for, I've got the word DF up here, but it's related to sample size. So a very small sample size, a slightly larger sample size, a slightly larger sample size, as big a samples as you could draw. And he found that they are normally distributed. They've all got a mean at 0. The standard deviation for them all is right around 1. But as the sample size gets bigger, the standard deviation it gets slightly smaller, as you can see here, that this dashed line is the smallest sample size and it's the most spread out, and then the solid line is the largest sample size and it's most spread out. What's the area under the curve? 1. 68%, 95%, 99%. So if we come out here, what's the probability of calculating a t out here? Less than 0.05. So when we calculate a new t-value, we compare it along this scale, and we ask, how far out into that tail do we get? And sometimes we have to consider both tails, because we've got a non-directional hypothesis, a two-tailed hypothesis. So we would need to add those together. Sometimes we can ignore everything below and only consider one tail. And so we could have up to 0.05 here. If we've had a directional or a one-tailed hypothesis. I know you've been using that terminology all quarter long. And this is why we call them tails, because it's the tails of this distribution. So here's just another way of looking at that. So that is a t-distribution. For this sample size, if we get to a t-value of 2.1, there's 95% of the population is between plus or minus negative 2.1. So we've got 0.025 under this tail and 0.025 area under that tail. Added together, that's your p is less than 0.05. So they have taken then that number, the 2.1, and put it in a table so that you can just look at it and say, if I get a t of greater than 2.1, then I'm going to conclude that I can reject my null hypothesis. I've used the abbreviation DF. That refers to degrees of freedom. It's usually related to sample size. It's the number of values in any calculation that are free to vary. So another way of saying that is how many numbers do you need to know before you know them all? If you know that you've got a group of 4 scores and it's got a mean of 5, and you know that this score 1 is a 4 and score 2 is a 4 and score 3 is a 6, you know what score 4 is. It is no longer free to vary. You can figure it out from this information. I kind of think about this also like when you're putting batteries into a radio, where once you put in the one battery, you know where the others have to go, what pattern has to be. When you pin down some of the numbers, the last number ends up being not free to vary. It's a little bit of an odd concept. For t-tests, your degrees of freedom is related to your sample size. So it's the sample size of group 1 plus the sample size of group 2 minus 2. So one of those in each of those groups is not free to vary. Our degrees of freedom is n1 plus n2 minus 2. This is with independent groups. With repeated measures, why have I only got one number for n there? Because it's only one sample, right? It's one sample. Each person's giving you 2 pieces of information. So for t-test with repeated measures. I have put all of the degrees of freedom formulas on this one slide so that you can come back to it. We're going to talk about those other 3 in a minute, but I just wanted you to have it all on one slide. Why don't you get out your clickers and let's see if you're understanding this. So we calculated that t of negative 2.97. What are our degrees of freedom? I'm seeing quite a bit of variation there. You don't all seem to be agreeing. Why don't you go ahead and turn to your neighbor and just confer and make sure that you've got the right answer. What's the formula? All right, you're changing in the right direction. Okay, you are almost all there now. So what are the degrees of freedom in this example? 8, 5 plus 5 minus 2. So let's talk about using that table of critical values. We are going to locate the row for the degrees of freedom. We are then going to ask the question, is the absolute value of my calculated inferential statistic greater than this critical value? We're going to keep moving right until we say no to that answer. Once we say no, we identify the last column for which we said yes. So we go back to the last column for which we said yes, and we go up to the column header, and that header contains our p-value. We need to know if the hypothesis was one-tailed or two-tailed, and we need to remember that our decision rule is p less than 0.05 is going to be considered significant. So, this isn't from your textbook. This is from the previous textbook I used for this class. I prefer it. Your textbook has one, and it's kind of backwards. I have posted this as a PDF for you to use. This is the more traditional way that it's presented in most stats books. Okay. What was the first step? So what are we looking for? Okay. What is the next step? Oh, you know what? Oh, well, no. What's the next step? What do we ask ourselves? Is the absolute value of my calculated inferential statistic greater than this critical value? So this is for that inane example between the first grade students and the second grade students. It was 2.97. What do we do? So yes, it is greater than that. What do? I move right. Is the absolute value of my calculated inferential statistic greater than this? Yes, I move right. It was 2.97. Is the absolute value of my calculated inferential statistic greater than this? Yes, I move right. Greater than this? No. I go back to the last column that had a yes, and I follow that column up to my significance level, and I go, oh, there are two of them. And then I say, oh, wait, there's an asterisk. I look at the asterisk, and it says, use the top significance level when you've predicted a specific directional difference, a one-tailed test, e.g., group 1 will be greater than group 2. Use the bottom significance level when you have predicted only that group 1 will differ from group 2 without specifying the direction of the difference, a two-tailed test. You guys understood that, right? So when we asked, is there a difference between ages of first grade students and second grade students, I think we just said it as, is there a difference between the ages? We didn't say, is this group older than that group? So let's say that we did a non-directional hypothesis. So what is our significance level? 0.02. So what's our decision rule? Less than 0.05? Are we popping the champagne? Yes, we are. Did we find a significant difference? We did indeed find a significant difference. So we would write this in APA style saying, T, that's the inferential statistic that we calculated, that's what it's called, has the degrees of freedom of 8. It was a calculation and it equaled 2.97. And then a comma. That is associated with a p-value of less than 0.02. Do we reject or fail to reject? We reject our null hypothesis. So we first off state our conclusion in terms of the null hypothesis, where we say we reject or we fail to reject. So we would say we reject our null hypothesis. You know what? Let me write this out. So for the first grade students and the second grade students, our T was 2.97. The degrees of freedom were 8. The P was less than 0.02. And so we would say we reject the null hypothesis that there was no difference in age between first and second grade students. How do we get to say that statement? We get to say that statement because we calculated a t with 8 degrees of freedom and it equaled 2.97, and that is associated with a p less than 0.02. So that statistic backs up that statement that we have made. So we state our conclusion in terms of the null hypothesis. We may be sure to name all of our variables. We then want to give the relevant means and standard deviations. And then we want to state it in incredibly plain language. We want to use causal words where causal words are appropriate. We want to use association words where association words are appropriate. So this is what we might end up with for that. So that was that first bit that I just written out. We then need to interpret it into completely plain language. Students in the second grade were older than first grade students. And I've got the means and the standard deviations. If I found that there is a difference between two groups, I can just look at those means and see which one was older or which one was faster or which group remembered more, because numbers have meanings. Before we move on, I want to acknowledge this sort of idea of mental gymnastics that we're doing, so if we've calculated a big inferential statistic, if we've calculated a small inferential statistic. For the t, what did we say was a small inferential statistic? 1, 0. What seems to be a big inferential statistic? So we can find a significant difference if it's bigger than about 2, but 2, 2.5. If I calculate a big inferential statistic, what is my associated p-value going to be? Is it going to be big or is it going to be small? It's going to be really small. It's going to be like p is less than 0.05. If I calculate a small inferential statistic, what is my associated p-value going to be? It's going to be large. It's going to be greater than or equal to 0.05. If I have a p less than 0.05, what happens to my null hypothesis? Do I reject or do I fail to reject? If I have a small inferential statistic that's got a large p-value, do I reject or do I fail to reject? If I have a large inferential statistic and a small p-value, am I concluding that this is a statistically significant difference? So am I saying that it is due to a real difference, or am I saying that it is due to chance? Whereas a small inferential statistic, any difference that I say is due to chance. Another way of saying this, it's a real difference. These seem to be two samples drawn from, from two different populations. These seem to be two samples drawn from the same or one population. It's a lot of gymnastics. You have to say, a big is a small and is a fail and is a good, So keeping those separate, making sure you understand what goes with what. When we conclude that there is a statistically significant difference, what we are concluding is that it is reliable, that it is repeatable. That we think we would find the same difference again and again and again. And here we don't know. Concluding that something is significantly different, statistically significantly different, is only saying that you think that it is reliable or repeatable. How about the proximity in the moral decision? I want to know. I've been playing this out for weeks now. Is it a reliable difference? Is it a real difference? Is it statistically significant? So there's our formula. There are means and sums of squares. We're going to plug those numbers in magically. Look, it's all going to calculate itself because you're never going to have to hand calculate a t-test. There it goes. It's calculating. Isn't that amazing? And we end up with negative 2.5. Does the negative mean anything? Nope. What's your impression right now, just from what you know about t's? You think it's significant? You're going to expect to find a significant difference? How are we going to find out? We're going to look it up on our table of critical values. What do we need? We need to know our degrees of freedom, right? Is this repeated measures or independent groups? Independent groups, right? You are either in one group or the other. So what are your degrees of freedom? $239, I had someone say it. $239. Okay. How do we use the table of critical values? What's the first thing we do? We need to find the row that's got our degrees of freedom. 239, 239, 239. Oh, it's not on there. I give up. Yeah. I had 127 and 114. Sorry. Either way, 221, 229 is not on there. I give up. Can we go home now? What are we going to do? Are we going to say we have more, or are we going to say we have fewer? Okay. Saying we have fewer is not lying. Saying we have more than we had is lying. Right? We don't want to lie. So let's go ahead and use that row for 120. What's the question you're asking? So you've got 2.5. You know what? I want you to get out your clickers. Let's see if I can line this up. Do you see? So an answer of A would be, I don't even get on the table. An answer of B would be, I think it's this column, C, D, E. Do you see it? Oh, I need to start a question, don't I? Okay. Okay, so how do we use that table of critical values? You've got 2.583. Your question is the absolute value of my calculated inferential statistic greater than this critical value? If we say yes, what do we do? Is the absolute value of my, do you remember, is the absolute value of my calculated inferential statistic greater than this value? And so what do I do? Greater than this value? So now what do I do? Go back. Okay? Did you all answer D? You're all answering D now. Really quickly. So that's the column we end up in. We come up to here to the significance level. Oh, we're at the same one. I think this time we had a one-tailed hypothesis. I think that our hypothesis was that, the closer you are, the less likely you are to kill one to save five. So if we've got a one-tailed hypothesis, what is our p-value? Less than 0.01. So what do we do to our null hypothesis? We reject our null hypothesis. And how might we say that in really plain language? What's the difference between those groups? Let me show you again the means. What might be a simple sentence that like a 10-year-old would understand? The people who had to push the guy were less likely to save the 5 innocent bystanders, mean 2.67, standard deviation 1.18, 19, than the group who simply had to pull a lever. So let's see, we would write something like this. We rejected the null hypothesis that there was no difference between the likelihood of saving the 5 innocent bystanders based on proximity to the one to be sacrificed. Do you see how we've got both of our variables in there? Here is how we get to say that. We then say, those participants who were asked if they would be willing to push someone said they would be less likely to save the 5, mean standard deviation, than those participants who were asked to pull a switch. Do you see how you got that? We doing okay? Yeah? All right, prove it. All right, and I'm seeing most of you there. And you know it's a 0 or a 1. You all know it's a 0 or a 1. If the difference between the group means is 0, is very little, then that calculation is going to be a 0. You know what? I'm going to skip that one. How about this one? When using a table of critical values, you keep moving to the right. If your calculated inferential statistic is all right, great, and I'm seeing you mostly there, and 85% of you are tired of me saying, is my absolute value greater than this critical value? Let's do some more practice. So if I have a t-test, oh no, my black pen has really ran out. That was repeated measures with a directional hypothesis. What are my degrees of freedom in this case? Do you need to pop back to that slide that's got all of the degrees of freedom on them? It's either 8 or 9, right? Because it's the n minus something. Repeated measures, you've only got one group, and it's n minus 1. So tell me when to stop. Okay. All right, I'm going to stop right there. And our t was 1.82. So what's the question we've got in our heads? Is the absolute value, is the absolute value of my calculated inferential statistic, 1.82, larger than that? Nope. So in that case, we haven't even talked about this, but I bet you can figure it out. What's the last column for which we said yes? We didn't say yes for any of the columns, right? We didn't get even on the table. So the answer to this would be A. We didn't get on the table. So A is I didn't even get on the table. All right? So what's going to happen to our null hypothesis? Are we going to reject or are we going to fail to reject? Fail to reject, because we're not even going to bother to go up and see what the significance level is. Because a t of 1.82 is, well, it's like right here, right? It's not into that tail at all. It's really likely, relatively likely, that our statistician friend pulled that out of his ping pong ball's bingo drum. So we would fail to reject, and we would say, so we would fail to reject the null hypothesis. Are we saying that there's a difference, or are we saying that there's no difference? All right, so there is no evidence that a difference exists. Yeah, well, so this is repeated measures, so that treatment 1 mean equals 16.75, standard deviation equals 1.8 is different from treatment 2, mean equals 13.14, standard deviation equals 2.5. Shall we do one more? Oh, yep. So that's like our sad sentence. There's no evidence of any difference. Let's do one more. Independent groups, non-directional hypothesis. Oh, that should be a lowercase n. Don't autocorrect. What are our degrees of freedom? So 45 plus 55, got to be 100, minus 2 is 98. Okay? Tell me when to stop. Oh, which one should we use? You think we should use 60? Because 60 is not lying, right? We have 60 degrees of freedom. We've got 98 degrees of freedom. So we've got 60, we've got 70, we've got 97. We've got 98. Do we have 120? No. So saying we've got 120 would be lying. So never lie. Even if it's like 119, you would go back to 60. Okay? Or you'd go and get one more participant. So we're going to use 60. T equals 2.78. What's the question we ask ourselves? Is it bigger than this? 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 Are we happy? And we're happy because we get to do what with our null hypothesis? Reject our null hypothesis. And we would write a sentence saying that this group, so which group performed better than the other group? So 16 better than 12 or 16 bigger than 12? I mean, this is very abstract. We don't even know what they're performing on. But if it was number of words remembered, you would say a very simple sentence like group 1 remembered more words than group 2. Yes? Okay? So, we've talked about comparing means, we've talked about calculating a t-ratio, we've talked about the properties and probabilities of a t-ratio, we've talked about critical values. Let's talk a little bit about statistical significance. We already said this a bit when we were filling out that chart. When we say that something is statistically significant, we are saying that we think if we repeat it, we would find the same results. That is all we are saying when we say something is statistically significant. If we repeat it, we think we would find the same results. We expect to find the same results. Another way of saying this is that the results weren't due to chance, that they were due to a real difference. Because if they're due to a real difference, if we look again, it's still going to be there, and we look again, it's still going to be there, we look again, it's still going to be there. Another way of saying this is that they are reliable. Reliable means repeatable. So those three things are three ways of saying the same thing, right? We'd expect to say this, that we could repeat it, it's reliable, they're not due to chance, they're due to a real difference. What statistical significance is not saying, it does not mean that it's a big difference, it does not mean it's an important difference, it does not mean that it's a valuable difference. So in our regular lives, when we use the word significant, it means important. In science, when we use the word significant, it means reliable. We calculated a statistically significant difference between ages of first grade and second grade students. That's not valuable, that's not interesting, that's not important. Is it reliable? Yes. But keep in mind that just because we say something is statistically significant doesn't mean that we're implying that it is valuable or large or important. Often in science, we will just use the word significant. We always mean statistical significance when we are using the word significant in science. And in fact, that's something that you want to really watch, is to make sure that you don't slip that word in to mean valuable or big or important, because in science, significant really does mean statistically significant. All right. Okay. So consolidating those ideas. This is what we went through already. So let's just look at it again. A large inferential statistic is associated with, is it a large or a small p? Small p. A large inferential statistic is associated with rejecting. Therefore, the difference is likely real. Yes. All right. And we would expect to find the same results. Okay? Got them? Don't move your heads too quickly because you don't want to fall out. I'm pretty sure that I posted like a blank one of these on SmartSite. I think it's in there called something useful. So I would highly recommend you copying that out and making sure that you can follow down one of those columns and know which column you're in. Okay? You got the t-test. You got it? It's in there. You're never going to let go of it. A very related idea, a very related inferential statistic is called the analysis of variance. And look what they did. They took the first letters of those words and they made a whole new word. And so this is also called an ANOVA. If you've got more than two groups, you can't calculate a t-test because you can't say the mean of group 1 minus the mean of group 2 minus the mean of group 3. That doesn't make any sense. So we need a way of calculating an inferential statistic that will allow us to see if there's a difference between more than two groups. And in this case, you would calculate an ANOVA. The ANOVA is abbreviated F. Because those statisticians, don't you love them? So the ANOVA, I think the F stands for Fisher. Does anyone? Yes, I'm here seeing nods. Fisher, big guy. So it's the F test or the F ratio. Just like so I didn't talk about why the t-test was called the t-test. Did I? No. So you'll hear it referred to as the student's t-test. And you might look at it and go, it's not mine. Don't give it to me. And it was developed by a guy who was working for Guinness Brewery and was wanting to do incredibly controlled quality control. Is this batch of Guinness the same as this batch of Guinness? Take 10 samples from this batch, take 10 samples from that batch, and compare them. And so he actually developed that formula of the mean of group 1 minus the mean of group 2. And Guinness didn't want anyone to know that they were that concerned about quality control and were using these sophisticated statistical analyses to determine their quality control. And so they didn't want him to publish his formula for his statistician buddies. And so he published it anonymously, and he just took on the pseudonym Student. And so he published it under the name Student. I don't know why he chose T. Do you know why he chose T? No, T. Okay. So each of these inferential statistics has a name or a letter that's associated with it. Before we talk about the F test, remember this chart? Oh my goodness. So, we were filling this out with our descriptive statistics. Now we can start adding our inferential statistics. We've talked about the t-test. Where does the t-test go? Does it go on row 1, row 2, row 3, or row 4? Row 3. It is a means comparison. You're comparing the means of two groups. So when you've got groups, categorical predictor variable, continuous outcome measure, it is normally distributed, you've calculated the mean and standard deviation, you're then going to calculate a t-test. Back to the ANOVA. We'll go back to that in just a second. Back to the ANOVA. If you've got more than two groups, you can't calculate a t-test, but we want to do pretty much the same thing. We want to compare the means of these different groups. So if we've got a predictor variable with more than two levels, that would give us more than two groups. If we've got more than one predictor variable, that would give us more than two groups. And so an ANOVA calculates the statistical significance for the main effects of each variable plus all possible interactions. So I was promising you that we would have that we would stop using this sort of decision rule and start having a rule of when do we determine that something is statistically significant. So the results would look like something like this, where you would have, for the main effective variable A, a calculation for degrees of freedom, a calculation for the F ratio, an associated p-value. And then for the main effective variable B, degrees of freedom, the calculated F, and a p-value. And then for the A by B interaction, the degrees of freedom, the calculated F, and the p-value. And so if you saw this table of results, so there's variable A, there's variable B, there's the A by B interaction. What is exciting about this table? So variable A, the main effective variable A, is associated with a very small p-value. Same rule. So if the p is less than 0.05, we would reject the null hypothesis. So there is a significant main effect of variable A. Is there a significant main effect of variable B? Is there a significant A by B interaction? Nope. This p-value is associated with, an F of 3.19. This p-value is associated with an F, really close to 0. This p-value is associated with an F really close to 0. The ANOVA, the F, is really similar to the t-test in what constitutes a large inferential statistic and what constitutes a small inferential statistic. So I'm just going to add that here if our F is more than about 2, or if our F equals about 0, or if our F equals about 1. We've been looking at results with ANOVAs kind of all along. Let me show you one of the examples that we looked at that used an ANOVA was that silver versus bronze medalists, agony versus ecstasy scale. We looked at this just last week, right, where we said, I don't think there's going to be an interaction. And sure enough, when we looked at it, we said there was a main effect. And here is where they are giving you that F value that allows them to state that there is a main effect. For the F test, there are two numbers for degrees of freedom. The first number has to do with the number of levels in that variable. The second number there has to do with the sample size. You're never going to have to calculate an F by hand. You're never even going to have to look it up on a table of critical values. So just being aware that it's similar. So you would write it like this, where you'd say, here's my inferential statistic. I calculated an F with the degrees of freedom of 1 and 72. It equaled 18.98. And that's associated with a p-value of less than 0.01, 0.001 in this case. Where does ANOVA go? Where does the F-test go? Does it go on row 1, on row 2, on row 3, or on row 4? It's kind of a trick question. Where does it go? Why am I saying it's a trick question? No. But it's categorical, continuous. It goes right here. What's the difference? How do you decide between these two? Two groups. More than two groups. What if I don't have groups? What if my predictor variable is also continuous? Hey, we talked about this already. This fits easy. You're going to calculate a correlation coefficient. That relationship between the two continuous variables. And so that calculated R that we've been talking about for weeks now is the inferential statistic if you've got two continuous variables. And just as a reminder, it can be negative, it can be positive. Oh! Sorry. In the case of the R, the sign of it, whether it's negative or positive, does matter. It's a critical piece of information. When it comes to the T, it doesn't matter. But when it comes to the R, it's a critical piece of information. Oh, I've got 2 more minutes, guys. So where does that go? Does it go row 1, row 2, row 3, or row 4? Row 4. We're calculating an R. That's what we're calculating there. When we are saying that an R is a big statistic, what is big when it comes to R? 1 is huge, isn't it? But even like 0.3 or 0.4, so like the absolute value of R is greater than about maybe 0.3. The absolute value of R is less than about, well, 0.2, I don't know. Because, and we will, all right, we will pick this up here after the break and look at the table of critical values for R. Have a nice Thanksgiving, guys.